Hello, welcome back to Educator.com and welcome back to Biochemistry. So today we're going to continue our discussion of amino acids by taking the next step. We're going to put some amino acids together, so we're going to be talking about peptides and proteins. Let's get started. Okay, so peptides and proteins, it's just a string of different amino acids like beads on a string. That's all it is, each one connected to the next. So let's write that down. Peptides and proteins are made up of amino acids, and again, I'm just going to write AA like that, amino acids strung together. That's it. Strung together. Now you're probably wondering, peptide, protein, what's the difference? The truth is there is no difference. There's just a bunch of names that are used for proteins, amino acids that are strung together. In general, if you want, you can think of a peptide as being anything less than about 10,000 atomic mass units. So a molar mass of about 10,000 or less. We tend to call it a peptide. A protein is 10,000 or more. And again, it's not really this. You can call it whatever you like. We're actually going to be using several terms interchangeably. So just to sort of throw it out there, protein greater than about 10,000 atomic mass units, or grams per mole, molar mass. Okay, now let's go ahead and talk about the formation of a peptide bond. The formation of a peptide bond. Very, very important bond. It's the bond that exists between two amino acids. And this is what holds the chain together. Okay. The bond between two amino acids. Okay. So let's go ahead and just take some generic amino acids and see what we've got. So we've got, again, when we write amino acids, I think it's best the backbone. It's the backbone that's important. Yes, the R groups are important, of course, when we're discussing them. But when we want to draw it out, it's the backbone that's connected, the peptide bond. So it's NCC, NCC, repeating units. So if you're going to write an amino acid, just start by writing NCC and then fill in the rest. So we have NCC. I'll go ahead and put H3 plus here. I'll go ahead and put the carbonyl there. And I'm going to write it in its fully protonated form, just so you see that this is actually it's a condensation reaction. The elements of water are going to be removed when we put these two amino acids together to form a dipeptide. Okay, so the carbonyl carbon is the second carbon. The R group goes here. The H is there. And then plus. And then, of course, we have, again, NCC. I'm just going to go ahead and this time I'm just going to put H there. Actually, you know what? Let me do it this way. Let me put an H here, and let me put an H here. I decided to this one, I'm going to not protonate. Don't worry about why. As far as where the H's go, whether it's 3 H's, 2 H's, things like that, that's not what's important right now. Right now, we just want to be able to get a global sense of how these bonds form. So we have an H here. This is the second R group, and we have the carbonyl. And this one I'm just going to go ahead and leave as an O minus. If you want, you can put an OH again. So now what happens is this. I'll go ahead and do an equilibrium arrow this way and this way. So when water leaves this, the elements of water are right here. Let me do this in red. Okay, the elements of water. So basically, it's going to be this carbon is the electrophile, and this nitrogen is going to be the nucleophile. Remember, the nucleophile is the one that actually has the electrons. It has the negative charge. Electrophile is the one that carries the positive charge. So this thing is actually going to attack this thing. We're not going to worry about mechanism right now. But that's what happens. What you're going to connect is, and I'll do this one in blue, you're connecting those two. You're connecting this carbon. So this carbon of one amino acid to the nitrogen of the amino group of the other amino acid. Okay, and in this direction, it is condensation because, again, the elements of water are removed. And we're going to go ahead and write out our dipeptide. And again, we're going to go NCC. Oops, those are stray lines. We definitely don't need those. NCC, NCC. Now, let's go ahead and put the H3. Let's leave that as plus. Let's go ahead and put an R group there. Let's put the H here. Here's our carbonyl. The N, let's go ahead and leave that one H that was there. This is our R2 group, right, of the other amino acid. Now we have this, and we have that. The peptide bond is this thing right here. That is your peptide bond. It is the carbonyl carbon attached to the nitrogen of the amino group of the amino acid to its right. So this is your peptide bond. Okay, and just to let you know, in this direction, it is hydrolysis. So when we actually add water to a peptide, it actually splits this bond right here, the peptide bond, and it releases two free amino acids. So in this direction, two amino acids, condensation. In this direction, it is called, got a little too much floating around here. So when H2O comes in, okay, when this H2O leaves, this, well, here, I'll just do this. In this direction, it's called hydrolysis. So that's it. Simple peptide formation. The elements of water leave. The carbonyl carbon attaches to the nitrogen of the other amino acid, and you get your peptide bond. And it goes on like this. So NCC, NCC, it's the second carbon. So if this were going to attach to another amino acid, it would be this carbon that's going to be attached. If this one were going to be attached to something to its left, that would be attached. That's all that's going on here. Okay. Okay, so under physiological conditions, interestingly enough, the equilibrium of the previous reaction of peptide bond formation, the equilibrium lies to the left. In other words, it lies to the formation of free amino acids, not the peptide, to the left. And the reason that's so is because the hydroxy group is not a good leaving group. And you remember that from organic chemistry. Just a straight hydroxy is not exactly a good leaving group. It doesn't just go away to make the reaction move forward and form the peptide bond. Good leaving group. The hydroxy must be activated. Must be activated. And if you remember from your first year biology course, or those of you that have already perhaps taken molecular biology, the amino acyl transfer RNA, ribosomes, protein synthesis, that's what is activated. It's activated with adenosine triphosphate and all that other stuff. So you're welcome to look that up. I'm not going to go through it here. So it has to be activated to induce it to leave. To induce it to leave. We just wanted you to know that in general, under normal physiological conditions, as is, the equilibrium tends to lie to the left, which is why you need it to be catalyzed.